So the next thing to talk about regarding polynomials are the derivative and integral formula of a polynomial. So first, we can write a polynomial as a sum. So this is just summation form of writing a polynomial where we let k go from 0 to n, where n is the order of the polynomial. The derivative formula basically for a polynomial for x raised to the power k, when we take that derivative, k comes down, and of course they've done a variable change from k to I because this is now derivative. So what was in the power comes down and multiplies the polynomial term, and then the polynomial term's power becomes whatever the previous power was minus 1. So you do this term by term. So remember, differentiation and integration are both linear operations. So if this is a sum, the sum of the derivative is the derivative of the sum. And so we can take the derivative of each term, and then we'll have another sum where we have derivative terms. Integral is the same way. When we integrate x to the I, it becomes x to the I plus 1. And now we're dividing by the I plus 1. And so once again, we would have a sum, taking the integral term by term, applying this formula. And then, of course, when we integrate, we have to add constant c. So the derivative and integral formulas for a polynomial are pretty basic. All right, so let's talk about rational functions. A rational function is the quotient of two polynomials. So we have some f of x is the numerator polynomial divided by the denominator polynomial. The roots of the numerator polynomial are referred to as zeros, and the roots of the denominator polynomial are referred to as poles. Once again, remember, a root is a value of x that makes the value of the function go to 0. The standard thing to do is to factor out a constant so that the highest order term in both the numerator and the denominator is 1. And so sometimes that means the function would be written as followed, where k is a constant and n of x and d of x are polynomials with the highest order term equal to 1. So that's pretty standard for a lot of reasons. First of all, this originates from control theory, which is where we get the term zeros and poles, and that's a common thing used in engineering in system controls. And then secondly, this makes it much easier to interact with MATLAB if you've already pulled the constant out. So partial fraction expansion is done on a rational function for a lot of reasons. One of the most commonly used reasons is when we're taking an inverse Laplace transform. It's commonly used in control theory as well as a technique to solve differential equations. So we won't discuss the Laplace transform yet. We will get to that later this semester. But what I do want to do, since we're discussing polynomials, roots, and rational functions, I do want to go over a little bit about how to do partial fraction expansion. So partial fraction expansion and how it's done depends on the type of root in the denominator polynomial. So the goal here is, if we have a numerator polynomial and a denominator polynomial, the goal is, first of all, to factor the denominator, and then to realize that this expression could have come from finding a common denominator of another expression where we have a single root in the denominator of a series of fractions that are then summed together. So basically, if we were presented with this function in equation 15.9, we could find a common denominator for that and write it as a single function as shown in figure 15.8. And we all know how to do that. Basically, it involves taking the numerator, multiplying it by all the other denominator terms, and then combining everything into a common denominator. What partial fraction expansion does is it goes the other direction. So we start with the function already simplified and already as a single function. And so the first thing we have to do is we have to find the roots of the denominator polynomial, and we have to write it in this way. So these P1, P2, all the way to Pn, those are poles. And in this case, they're simple poles, meaning each one has a unique value. And then assuming, first of all, the big assumption in partial fraction expansion is that the numerator, the order of the polynomial in the numerator, has to be lower than that in the denominator. So once again, the goal in partial fraction expansion is to get from the expression here in equation 1548 to the expression here in equation 1549. And as I said, it depends, your approach depends on really how you proceed. So if you have real repeated roots, meaning when you factor you get something like an s plus 2 squared, then we have to do the partial fraction expansion differently. So if you have n repeated poles at some value of minus p, then basically the way you write the partial fraction expansion is decreasing powers of n with that pole s plus p. So if, for example, and we'll do an example problem on this, but if you had s plus 2 cubed as one of your terms, then your partial fraction expansion would be s plus 2 cubed plus something over s plus 2 squared plus something over s plus 2. And then you have the rest of the terms in that function f of s. So it is possible to have repeated poles or higher order poles, and in that case you have to do the partial fraction expansion differently. And then finally, the final option is that your roots of your polynomial generate complex conjugate pairs. If you do have complex conjugate pairs, then the easiest thing to do in the partial fraction expansion is to leave the denominator as a squared term and realize that the numerator then will have to have a term in s. So you would take your s squared plus as plus b, and then in the numerator you would write that as a1s plus a2, and then you have the rest of the function being expanded. So f1 of s is the remaining part of the function that didn't have the pair of complex conjugate roots. It's also good to show how we would complete the square, because completing the square makes it possible to do some applications later that will be important. So if we have a quadratic function s squared plus as plus b, we realize that a perfect square would be of the form s squared plus 2 alpha s plus alpha squared. And because that's not what we have, we know that we're going to have some beta squared, which is going to be a subpart of this coefficient b. So we can take this first part and factor it as x plus alpha squared, and then whatever is left is beta squared. Then we can also look at the numerator, and we can write that as a1 times s plus alpha plus some other constant b1 times beta. If we do that, then we can split this into two functions where we have the s plus alpha part in one part and the beta part in another part, and our constants a1 and b1. Once again, the reason for doing this will become clear when we look later in the semester at the Laplace transform, but right now we're just trying to teach the technique on what to do with the polynomials. So I'm going to end the lecture here, and then we will look at some examples.